Okay. Yeah, so today we're going to talk about braid groups, which are fundamental groups of configuration spaces. So we're going to talk about some examples of configuration spaces that are Eilenberg-MacLane spaces, and then we'll talk about what the fundamental groups are. Okay, so so by definition, we're going to define the pure braid group on k strands to be the fundamental group of the ordered configuration space of k points in R2, and the regular braid group to be the fundamental group of the unordered configuration space. And more generally, we'll define the pure braid group and the braid group of manifolds to be a manifold to be the configuration space, or to be the fundamental group of the configuration space of ordered or unordered points in that manifold. Yeah, so what's an element of the braid group? Well, it's an element of the fundamental group, so you need to pick a base point. So up top here, this you should think of as being, this is just some point in the configuration space of, 6 points in R2. So that's our choice of base point. And then an element of the fundamental group is an equivalence class of paths from the base point to itself. So I'm sort of drawing the time direction vertically. So at each vertical slice, you get an element of the configuration space. So note that these, we're not allowed to have, if we had one more point, we are not allowed to have like a path like that, because what we want is that every horizontal slice gives you an element of the same configuration space. And here, if you took okay, that one worked. I guess I can move it. If you took a slice like that, you would get, 9 points, and if you took a slice like that, you'd get 1 point. Yeah, so if we forget this one, then what's the path? You just look at a horizontal slice, and at each slice you get an element of the configuration space. So this whole thing is a picture of a path. Any questions? Okay, and it should, it's called the braid group because this looks like a braid. And so the pure braid group, the points are ordered. You might as well pick. At we're gonna pick some base points. So maybe all the points are in a line, and the ordering. Might as well pick all the points in a line, and the ordering from the line agrees with the ordering on ordered configuration space. So what does it mean to be in the pure braid group? Well, if a strand, this whole thing this picture needs to be a loop, not just a path. So if so the strands need to end up where they start. In the previous picture, the second point can move to the third point, but here the second point needs to come back to the second point. Otherwise, it wouldn't be a loop in the unordered, or it wouldn't be a loop in the ordered configuration. And here, this gives you a loop because the points are indistinguishable. So the second point moving to where the third point is, results in the same element of the configuration space. Any questions? Okay. So, geometrically, what does it look like when you add, like what's the group structure in the braid group coming from concatenation in the fundamental group? Any guesses? So if you have two braids, what does their sum look like? Yeah, you just like tie them together. So I'm writing plus just because in Microsoft Paint it's hard to make like a time symbol, but like this won't be abelian because it's, or in general it won't be abelian because it's a fundamental group. Yeah, so if you have one braid, you have another braid, you just stack them on top of each other and glue them together. I guess, because it's a fundamental group, you reparameterize. I didn't draw this reparameterized. Yeah, so this, I assume this is what you meant by tie? Yeah, so you just put that one there, and then this one here. And same for ordered configurations. Okay, so what's the unit? Any comments? Or any guesses?
Just a bunch of straight lines?
Yeah, just a bunch of straight lines. That's the unit. I guess this is a picture of the unit in the pure braid group, but in the other one, just delete the labels. Yeah, and then I don't have a picture, but if you stack it, if you stack a bunch of lines, just cross this one out and replaced it with a bunch of straight lines, then this picture is going to be terrible, but you would just look like that, and these two loops aren't, or these two paths aren't the same, but they're homotopic because you just sort of contract the constant part of the path down, and then they're equal. Yeah, okay. So the constant path, which is pictorially as straight lines, is the unit. Okay. So, and one thing to say, there's a short exact sequence of, the pure braid group maps to the braid group, which maps to the symmetric group. Do I have a picture? Oh, yeah. Maybe before giving the proof, let's just sort of see what it is geometrically. So which which permutation should this go to? So this is an element of the braid. Oh wait, sorry, this is an element of the pure braid group. That is not what I wanted. Yeah, so type that. Which permutation should this go to? So like 1 should go to what? 2 should go to what? 3 should go to what? Etc. So how do you, any guesses? We want a homomorphism from the braid group to the symmetric group. So given an element of the braid group, we want a permutation.
Send each point to where it ends up.
Yeah. So, first point, if this point is number 1, send it to 1. This point ends up at the third point, so it goes to 3. This third point goes to 2. Fourth goes to the fourth. fifth goes to the sixth. Yeah, and so, you know, here in the braid groups, like we've picked a base point. So these points aren't ordered, but we've picked a base point. So if we have a base point, you can order them. The worst part of annotate is the hard to get to the text thing. Yeah, so you just see like 1 goes to 1, 3 goes to, you know, 2 goes to 3, etc. And the pure braid group is exactly the kernel, because here, you know, 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4, etc. Okay, so how do we rigorously show there's this, you know, I guess that gives a map, and it's clear that this is the kernel of the map. Yeah. But you know, how do we see this rigorously? Well, ordered configuration space is a covering of unordered configuration space. So, you know, we get a long exact sequence of homotopy groups, and I guess this is trivial. You know, whatever you can call them 0 or 1. I guess this is a set. So yeah, the like high 0 of SK is just SK. Maybe I should have written 1. You know, this is just the braid group of M. In the case M is R2, it's the regular braid group, and this is the pure braid group. Okay, so you know the long exact sequence in homotopy groups associated to this covering. Yeah, so this map is just to forget the order on the points map. Gives you this long exact sequence, which is exactly, or gives you the short, you know, gives you a long exact sequence that contains this short exact sequence. Okay, so remember, you know, Eilenberg-MacLane space. Today we're just talking about KG1s. So KG1 is a space whose fundamental group is G and whose higher homotopy groups are 0. I guess it's a connected space. And we talked about, I don't know, a few weeks ago that a space is a space X is equivalent to a, or you know, I guess I would read this as is a Eilenberg-MacLane space for its fundamental group if and only if the universal cover of X is contractible, you know, or has trivial homotopy groups, at least. Yeah, and the way you prove this theorem is by looking at the long exact sequence of homotopy groups and the universal cover. You look at the long exact sequence of homotopy groups for the universal cover mapping to X, and will tell you, and if the universal cover is contractible, it'll tell you that the fundamental group is the only homotopy group. And there's sort of functorial constructions of the KG1s, but they're these Eilenberg-MacLane spaces are only this notation means sort of a homotopy type, or like any space with this property. So they are unique up to homotopy is something we proved. Okay, I guess we didn't prove in the n=1 case, but it's also true. Yeah. So theorem that says if if M is a connected 2-manifold that happens to be an Eilenberg-MacLane space, then the configuration space of k points in M is an Eilenberg-MacLane space. For the order, the ordered configuration and the unordered configuration space are both Eilenberg-MacLane spaces. Yeah, so if you just take any surface that's an Eilenberg-MacLane space and look at the configuration space of points there, it'll be an Eilenberg-MacLane space. And then something that's maybe well known to some of you and maybe new to other of you, the if you have a surface, it's an Eilenberg-MacLane space, unless the surface is S2 or RP2. Is there? I'll probably explain this anyway, but are there some people who like are seeing this for the first time? This second theorem. Or, you know, has everyone seen that the like a explanation that surfaces other than these two are Eilenberg-MacLane spaces? Okay, I can't tell. It seems like people have seen a proof of this theorem, but I'll just sketch it anyway. Yeah, so like, how do we see that the torus is an Eilenberg-MacLane space? Well, we just need to see that its fundamental group is contractible. Well, the universal cover of the torus is R2. How do we see for the Klein bottle? Well, this is the Klein bottle. So how do we see that? It's an Eilenberg-MacLane space. Well, the torus covers the Klein bottle, so the universal cover of the torus and the Klein bottle agree. Yeah, so if you have nice spaces, the universal cover of a cover will be the universal cover of the base space. Yeah, so you can think of, how would you think about it? Well, the Klein bottle is like R2 mod this equivalence relation. So you can think of the Klein bottle giving, the universal cover of the Klein bottle being R2 is saying, hey, we can tile R2 with tiles like this. And then the if you cross out this, I'll use a different color. If you cross out this middle line, then this gives you the usual tiling of R2 corresponding to the universal cover of the torus. I'm going fast because everyone said they have seen this before, but I can slow down if this is not familiar. Is this familiar to at least someone? Okay, at least one person familiar. And then, how do you do it in genus bigger than one? Well, one way is with hyperbolic geometry. You can see that the universal cover of surfaces in higher genus is the is R2, but like geometrically viewed as the hyperbolic plane. So here's like a picture of the disk model, and we need to tile hyperbolic plane. I guess this is a genus 2 surface, so we need to tile it with octagons. And so if you tile it with triangles, and then this is like the tiling associated to like the fairy graph, and then you ignore the red, you get a tiling by octagons. So I only drew one of them. I should have drawn 2 of them, but the second one would be too small for my art skills. Yeah, and this is how you see sort of that the genus 2 surface has R2 as the universal cover. And then for open surfaces deformation retract onto a graph. So, here's how you do it in a genus 1, genus 2 surface with 2 punctures. Yeah, so non-compact surfaces are homotopy equivalent to graphs, which are Eilenberg-MacLane spaces for free groups. Okay. Yeah, so theorem we want to prove. So we have some manifold that's homotopy equivalent to, we have a 2 manifold, then it's an Eilenberg-MacLane space. Then for all k, the configuration space is an Eilenberg-MacLane space. And yeah, and maybe, if you're bored, think about what's going to go wrong if the dimension of the manifold is bigger than 2. Okay, so how are we going to prove the theorem? Well, the first lemma is says if you can prove it for ordered configurations, then you can prove it for unordered configurations. Yeah, so this cuts the work in half. This says we just need to worry about ordered configurations. And what's the proof of the lemma? The proof of the lemma is look at ordered configurations mapping to unordered configurations. That's a covering space. So the universal cover of these two spaces agree. And so, if the universal cover of ordered configuration space is contractible, the universal cover of unordered configuration space is contractible because they're the same. Oh yeah, apparently for pathological spaces, the composition of two covers is not a cover. Someone who ran for governor of Illinois made this mistake in some published paper. He didn't win the primary. I think he came in third. Okay. Yeah, so the next lemma basically, this lemma is basically trivial. So it says, if the manifold's an Eilenberg-MacLane space, then the configuration space of then the ordered configuration space of 1 point is an Eilenberg-MacLane space. Well, what's the proof of this lemma? The manifold is homeomorphic to the configuration space of 1 point. So, yeah, so that's basically saying this theorem is trivially true when k is 1. So, we're going to prove it by induction, and this lemma is just saying the induction beginning is true. Because if you have 1 point, it's just the configuration space of 1 point is just the underlying space. So, that's an Eilenberg-MacLane space, so is this. Okay, the next lemma involves these forget point maps. Yeah, so what are they? So if you have k plus 1 points, you can just remember, and they're ordered, you can just remember the first k points. So a lemma just says this is a fiber bundle, and the fibers are given by the manifold minus k points. Yeah, because what do you have? You have k points in your manifold, and you're asking what collection of k plus 1 points maps to it. Well, M1 through MK are determined by M1 through MK, but and the only question is, where is MK plus 1 going to go? And it can just be any point in M other than M1 through MK. So that's, I guess, why the fibers are this, and then it's it's possible to check that this is a fiber bundle. Okay. So yeah, we have enough lemmas. So now we'll prove the theorem. So first lemma said it suffices to prove it in the ordered case. The next lemma says it's true for k equals 1. So let's assume it's true for k and try to prove it for k plus 1. Well, this maps a fiber bundle, and the fibers in the base are Eilenberg-MacLane spaces. So if you look at the long exact sequence homotopy groups, you get that the middle space is an Eilenberg-MacLane space. I didn't write out the long exact sequence, but it's you just write it down, and it's immediate that that if the base and the fiber are Eilenberg-MacLane spaces, so is the total space. Any questions about the proof? Okay, so you can also use these long exact sequences to compute fundamental groups. It seems like I horribly timed this lecture, and I'm going twice as fast as I thought. I think it took me a ridiculously long time to make all these paint pictures. So I'm I spent 5 hours prepping this class. Normally, if I spend 3 hours prepping a class, I've produced enough material. But the amount of time it takes me to make the paint pictures versus the amount of time it takes to look at the paint pictures is different. Whatever. Okay, worst case we end early. Yeah, okay, so you can use these long exact sequences to compute fundamental groups. Yeah, so the first theorem says that if the oh yeah, maybe before we say this, so what goes wrong if the manifold is bigger than two-dimensional? Yeah, let's say you start out, there are plenty of high-dimensional manifolds that are Eilenberg-MacLane spaces, so let's say M is like a 7 manifold that's an Eilenberg-MacLane space. What goes wrong here? So, particularly like what if M is just R7? Why are configurations of 2 points in R7 not an Eilenberg-MacLane space?
You can like unwind stuff, right? Because you have like no nodding, basically.
But what breaks in the proof? Like what's yeah. Is this line fine? Yeah. Anyone think that like I'll just circle the sentences and people can. Okay. Yeah, so let's say we're just going to think. Yeah, so let's just say we're taking M is R7, and I'm wondering like what goes wrong. Okay. You're allowed to do induction, so that's fine. You're allowed to consider something. So okay, I think there are three sentences with content. Yeah, and M is R7. So which sentence doesn't work for R7? Or, do any of these sentences work for R7? I'm going to go check my email while people think about this. This is good teaching on my part. Now, yeah, so what's the proof of the green? Yeah, so the let's go back and see like does the green need M to be two-dimensional? So what's the proof of the green? The green is the green is this lemma. So it says like if this is an Eilenberg-MacLane space, then that's an Eilenberg-MacLane space. Yeah. So does this proof ever use that the manifold is a surface? Yeah. So we're assuming this is an Eilenberg-MacLane space, so we're assuming this is has a contractible universal cover. The universal cover of this is that has this map. All we're using is that this is a contractible universal cover, and this map is a covering that doesn't use anything about what the manifold is. Okay, and then the next lemma says if that it's true when k is 1. So it says if M is an Eilenberg-MacLane space, then the configuration space of 1 point is an Eilenberg-MacLane space. Does this use the dimension of the manifold? No, just manifold is always homeomorphic to the manifold. So what goes wrong is, I don't know what color it was, this long sentence. So this map is still a fibration. But what's the, what are the fibers of F? F are, so in this example, what are the fibers of F? Or for this F? So I'm not looking for like, okay, so the fibers of F are just M minus K points. M minus K points. So we're assuming M is an Eilenberg-MacLane space. Why is M minus K points an Eilenberg-MacLane space? So in dimension 2, dim M equals 2, why is M minus K points a KG1? So one thing to say is K K is at least 1. So so which surfaces are not Eilenberg-MacLane spaces? Yes. Okay. So people said they knew the answer to this. So which surfaces? Yeah. What are the okay? So
Sphere.
Yeah, sphere and RP2.
Just
Is it possible? So like the key thing we're using is that M minus K points is not RP2 or S2, right? Like, so we're assuming that M is not RP2 or S2, but if you take a manifold that is not, if you take a manifold and subtract points from it, you're going to get something that's not RP2 or S2. I guess the only way you can get RP2 or S2 by taking a surface and subtracting points is if you start out with RP2 or S2 and subtract 0 points, right? And we're here in the induction, we're subtracting at least 1 point, and we're not starting out with RP2 or S2. So that's why the fiber is going to be an Eilenberg-MacLane space. So what happens in the R7 example? So what is like R7 minus 1 point? What is like a name for the, what is a well-known space with this homotopy type? Yeah, the sphere. So this is just S6. And so, here, like R2 minus 1 point is S1, which is a KG1. It's a G equals Z. But if you take, if you're in higher dimensions and you subtract points, there's no reason for them to be Eilenberg-MacLane spaces. S6 is not an Eilenberg-MacLane space because no, it's not a KG1 because pi 6 is non-trivial. It's not a KG6 because pi 7 is non-trivial. Yeah, so this is what goes wrong. So like this map is still a fibration, but so all the lemmas didn't use that the thing was the surface, but the way we're applying it is, because what we're using that the fibers are the fibers are the manifold minus points, And so those are going to be Eilenberg-MacLane spaces because we're in dimension 1. So in general, it turns out that M minus k points, let's say, is well, okay, so there's two cases. So let's say if M is compact, then M minus k points is M minus 1 point wedge S wedge like I don't know, k minus 2 copies of Sn minus 1. So if you start out with a compact manifold and you remove a point, first what you do is you just kill the top cell. So you just sort of, you remove 1 point, you make M, you change the homotopy type of M to be just like that of its n minus 1 skeleton. And then so once it's non-compact, each point you remove up to homotopy has the effect of wedging on an Sn minus 1. So, R7 is not compact, so when we subtract a point, that has the effect of adding a S6. Yeah, so even if you start out with an Eilenberg-MacLane space, these Sn minus 1s, assuming n is at least 3, wedging these on is going to produce non-trivial higher homotopy groups. And so this is why the proof breaks in higher dimensions. Any questions? Okay. Great. I feel like I should force people to be more interactive. Okay. Oh yeah, so then the comment is we can use these long exact sequences to compute homotopy groups. I'll just sort of tell you what happens. So if the manifold is bigger than 2-dimensional, then this braid group is just the fundamental group of the manifold to the kth power semi-direct Sk. Yeah, so so the symmetric group so the semi-direct product, we need to have the symmetric group act on this, and the symmetric group acts on kth powers of things by permuting the terms. So that's the action defining the semi-direct product. Yeah, and then for surfaces you can completely calculate everything. I'm just going to tell you what happens, or I guess first I'll just tell you what happens for the braid group. So for the braid group, there are k minus 1 generators, and there are these two kinds of relations that say that like certain generators commute and certain generators don't commute with each other. So what's the slides are in the wrong order. So let me let's just talk about like what's a group presentation. So if you have a group, then what's the presentation for that group? Well, you pick elements in your group. I guess these are finite presentations. You can define it for infinite, but it's easier to write it out in the finite case. So a presentation of a group, you pick elements G1 through Gn in your group, and you let and then you consider the free group on the same number of elements, and then the data of a presentation is these generators and these words in the free group. So we say this is a presentation if the map sending AI to GI induces an isomorphism like this. So to get a map Fn to Gn, what do you need to do? Well, you just need to specify where each of the AIs go. And so, here, we've picked the set. So the fact that this map is surjective means that G1 through Gn generates G. And then the fact that R1 through RM are words in Fn, and these are going to be relations, so these are going to be things that map to 0 in G. And so we say it's an isomorphism if this map factors through this quotient. So here I mean the normal subgroup generated by these elements. So this is the intersection of all normal subgroups containing these elements, or the subgroup generated by conjugates of these elements. Yeah, so basically what does this mean? It means every element in G can be written as a product, and these words R1 through RM are satisfied in G, and any in fact any relation between these generators comes from these words R1 through RM. Yeah, so for example, if you just take G1 through Gn and no relations, you just get the free group. Or maybe I should have called this A1 through An. Yeah, if you have a bunch of elements and no relations, it's the free group. Here's another example. So Z plus Z mod 7. One presentation, we can take G1 and G2, and so we want this group to be abelian, so we're going to insist that G1 and G2 commute. So that's this condition. This says, if you can, so this being a relation means this word equals 1, and if you rewrite the equation thing in red equals 1 out, you just get that G1 times G2 is G2 times G1. And then we also want the second generator to have 7th power trivial, so we just add G2 to the 7th. Any questions? Yeah. Okay, sorry, the slides are out of order. Yeah, so this is a presentation of the braid group, so I need to tell you what these sigma 1 through sigma k's are, and so the sigma I is the braid that just braids the ith strand over the I plus first strand. So we're in unordered configuration space, so these things aren't ordered, but we can we can pick a base point where all the points are in a line, and then they get an ordering from that. So that's what I mean by the ith point. And yeah, so we just braid the ith point over the I plus first point. So if you want to think of this as 2 points moving around, it's like you have these 2 points, and then they do a half twist. Okay. And okay, so what are the relations? So the first kind of relation says that that these sort of elementary braids, these commute with each other as long as the index is far enough apart. So what this is saying is if you braid the I have a better picture. No. Yeah, so if you braid the, here we're braiding the 4th point over the 5th point, and then we're braiding the 2nd point over the 3rd point. So, and then we add them, so we just connect everything up. And then, okay, that should be the same as if you do it in the other order. So you first braid the 2nd point over the 3rd point, and then braid the 4th point over the 5th point. And why are these the same? Well, what you can do is you can sort of move this thing downward and move that thing upward. Does that make sense? Okay, makes sense to one person. Michael, did you already know this like beforehand? This is a test of like if I'm actually communicating. Okay, so at least if you already know this, it is understandable, which it is possible to explain something so poorly that people who understand it ahead of time don't understand it, don't understand your explanation, so at least I passed that bar. I haven't confused people who knew about it beforehand. Great. Okay, so now, what's this relation? Well, it says you add you braid the fourth over the fifth, and then the third over the fourth, and then the fourth over the fifth again. So this left-hand side are these three pictures, and then when you add them together, you get this picture. On the other hand, the right-hand side are these three pictures, and when you add them together, you get this picture. That is what is, and then how do you get from this picture to that picture? You sort of pull this. I don't know. You sort of take this red thing, which is behind everything, and push it to the right behind everything, and you get that strand. Yeah. Okay. And so, the statement is not only, I guess it's reasonably easy to see that these are elements of the braid group and they satisfy these relations. If you want to rigorously prove that these generate out everything in the braid group and that these are all of the relations, you would look at these long exact sequences and homotopy groups coming from these coverings and these forget the point fiber bundles. Yeah. So from this, you can read off, from a presentation, you can read off an abelianization. So, recall that the that H1 of the so H1 of the configuration space of K points in R2 is the same thing as the or H1 for a connected space is just the abelianization of the fundamental group. And the fundamental group by definition is the braid group. So H1 of configuration space is the abelianization of the braid group. So what do we get? You get these generators and these two relations. And then once you abelianize, well, when you abelianize this relation somehow, or this relation is already included in the fact that the generators commute. So when you abelianize, you just declare that the generators commute. And okay, so all we have is this other relation. And now when the generators commute, we can cancel things. So we can cancel this sigma I with that sigma I, this sigma I plus 1 with that sigma I plus 1. And what are we left with? We're left with, the sigma I is sigma I plus 1. So what this says is that when you abelianize, all of the generators are the same. Because this relation after abelianization just says sigma I is sigma I plus 1. So this tells you that the braid group is just Z. Sorry, that the abelianization of the braid group is just Z for K greater than or equal to 2. The braid group is the trivial group for K equals 0 or 1. So that's pretty straightforward. And then I claim that this Z is exactly pi 3 of S2. Yeah, so anyone remember how that argument went? Okay, yeah, so scanning is going to say that this is the same thing as H1 of a of some component of loops KS2. Maybe it's better if I type. And this is going to be the same thing as the fundamental group of loops to S2, because the fundamental group is abelian. The fundamental group is abelian. Well, why is the fundamental group abelian? Well, because this is the same thing as pi3 S2. So that's why it's abelian. And then the homology is just the abelianization of the fundamental group. Yeah. So this scanning mapping of homology equivalence in a range gives us a natural isomorphism once k is at least 2 to this homology group of this loop space, which is the same thing as pi3 S2. Yeah. Okay. Any questions? Great. Oh yeah, and so you can do the same thing for configurations in H1 of conv k RD. Let's say take D greater than 2, then H1 of this is going to be, well, it's going to be, and we'll take k greater than 1, so this is going to be SK, abelianized, and the abelianization of the symmetric group is Z mod 2, and then the same argument says that this is pi D plus 1 SD. So, another way to think about this, this homotopy group is that the, pi3 S3 is the abelianization of the Braid group, which is Z, and pi, pi for D bigger than 2, pi D plus 1 of SD is going to be the abelianization of the symmetric group, because that's the fundamental group of configuration space. I1 of k. RD is, it's the Reith product of the fundamental group of the manifold with the symmetric group, and so the manifold's simply connected, so you just get SK. Yeah, so this, this unstable homotopy group that's Z and then Z mod 2s, that corresponds to abelianization of the Braid group being Z, and then abelianization of the symmetric group being Z mod 2. Okay, yeah, the topic for Thursday and next Tuesday is scanning for configuration spaces. Okay, so the next example is the two-sphere. So for the two-sphere, we if you work it out, you get same generators. Was there a comment in chat? No, I don't know what that was. Okay. You get the same generators, you get the same first two relations, and then you get this extra relation here. Oh, I guess I'm writing not equals 1. Okay, so I drew a picture in as if this were the Braid group. So the Braid group of R2. So this black circle is maybe my picture of R2. And so what is this extra relation? It's you braid the first over the second, then over the third, then over the fourth, etc., and then you unbraid. So that ends up being this picture. Any thoughts on, now let's imagine that, I don't know how to draw this. let's say the black thing is really a two-sphere. It's a terrible picture. Okay, the black thing is a two-sphere. It's no longer a disk. So why is this relation? How can we unwind this braid if we're working in the two-sphere instead of just R2? That's helpful. Yeah. So maybe I'll just say, just imagine that this black disk, this black disk is a disk in a two-sphere. How can we use the rest of the two-sphere to unwind this? Or, does anyone want to claim that they see it even if they can't draw it? Okay. Let's think, okay, we've got the two-sphere. We got our points. And then what is this? This is one point goes all the way around the other points, I think. But now this black thing is a two-sphere. So why is this loop trivial if we're in the two-sphere instead of R2?
You can just pull up, right?
You can just go around the other
Pull
way,
the loop up.
right? Like, yeah. You just make it bigger and bigger. The screen is terrible. Okay. At the green. You contract it the other way, right? Someone should tell me they don't get this picture. Yeah, so, okay. Okay, so one person sees, yeah. Yeah, so if we maybe draw it, again, we got the dots, and now this is, one of the dots goes all the way around. Let's move the dot down a little bit. And now it goes all the way around, and then there's stuff, oops, killed my picture. I don't know what happened. I'm going to redraw this. So we have a bunch of dots, and then one of them goes around the sphere, and you can just lower this picture. You can just unwrap this picture around the other way on the sphere. I don't think I'm going to get a better picture, but if someone is confused, feel free to ask me to try to explain it again. Okay, so yeah, so that's the presentation of the fundamental group of configurations of points in S2. That's not an Eilenberg-MacLane space, but still has a fundamental group. Yeah, so a corollary is we get that for k at least 2, H1 of the configuration space is Z mod 2k minus 2. So what's the proof? Well, H1 is the abelianization. Here's a presentation. And, we just declare that all the generators commute. And the first, the first relation tells us nothing. In the abelianization, the second relation tells us that all the generators are the same. And then what does the last relation tell us? Well, all the generators are the same. So what do we get? We just get all of these terms are the same, and how many terms are there? There's 2k minus 2 terms. So this says 2k minus 2 times any of the generators are 0. This is a typo. I guess this is like a sigma I. Okay. Yeah, so the first relation tells us nothing. Second relation tells us the generators are the same. Third relation tells us 2k minus 2 times the generators are 0. So that's exactly, we we have one generator, so that's Z, and then 2k minus 2 times the generator is trivial. Yeah, so why do I care about this? Well, one thing it says is homological stability fails. So I guess we just spent the previous 2 classes proving homological stability. So what's different about S2 versus, like why doesn't this contradict something we proved last class? Like, preferably someone other than Zach answers. Yeah, so like what was our assumption? What assumptions did we make on our manifolds to prove stability? Oh yeah, or first maybe why does this mean homological stability fails? Well, what is this group? This group depends on K. So it's not, stability should mean it eventually won't depend on K. Oh yeah, so Michael said like the manifold needs to be non-compact. Yeah. So what was our map? I should have had one more slide. We have this, we have this manifold, and we got a bunch of points, and then we used that the manifold was non-compact to add one new point near the boundary. We sort of pushed everything away from the boundary, and we added one new point. Well, S2 is not compact. Or sorry, S2 is compact. It's not compact. So you got a bunch of points in a 2-sphere. Like, how are you going to add one more point in a continuous way? There's not an obvious way to do this. And so, the fact that, we used non-compactness to define the stabilization map, but you might think, okay, we're just being lazy or not clever. And yeah, but so this shows to some extent, it wasn't just that we were being lazy and like we couldn't think of a map in the compact case. Like the theorem we're trying to prove is just false. Like there just isn't, these groups are going to depend on K. Yeah, these groups keep changing as K changes. Oh yeah, so I guess 2 weeks from today, is that correct? Zach is giving a talk. Zach, is that right? Hopefully.
I think so.
Okay, yeah. And like part of the purpose of the talk will be to say that it looks like things aren't stabilizing, but you do have some kinds of stability. Like if you reduce this mod 3, then the sequence is going to look like 0, 0, F3. This is a terrible color. Look like the sequence is going to look like 0, 0, F3, 0, 0, F3, 0, 0, F3, 0, 0, F3, depending on whether or not 3 divides 2k minus 2 or not. So with field coefficients, or with F3 coefficients, it's not eventually constant, but there's a pretty clear pattern. And like Zach will talk more about that. And then I think 2 weeks from Thursday, Nick is talking. Ideally, or if anyone else wants to give, I guess they're talking about their research. If anyone else wants to give research talks, like I guess like Michael, you study operads or something. So if you want to give a talk, someone on your research, at some point, like maybe the last week of classes or something, tell me. Also, if people, either senior or more junior grad students, want to give expository talks, possibly in groups, tell me. I think it might be nice if, you know, I'm happy to like suggest topics and meet with you guys. Because I think, you know, I think people learn more if it's interactive. And I'm lazy and don't want to teach, so I want to try to make other people teach my class for me. But yeah, so feel free to contact me if you would like to give a presentation at this class, like, you know, week after Thanksgiving or something. Okay, I'm